Hello everyone, this is Mike McGinn, your instructor for NETI115 routing and switching. And this is a overview presentation for chapters 1, 2, and 3. The purpose of these overview presentations are not to go through the content on NetICAD slide by slide, but to just hit some of the high points, especially at the conceptual level. On the subjects that we are covering in this course, the actual configurations and learning how to configure the devices, the exercises, the packet tracers, etc. do a pretty good job of that. So in these presentations, I'll stay clear of actually teaching you how to configure devices and basically help you understand the concepts behind why we are doing those things. So with that, I'm going to share my screen, and we're going to start off on talking about a few slides in Chapter 1. In Chapter 1, in Slide 1.1.1.2, they talk about a converged network. As you probably recall, this was touched on in NETI115. Converged network basically allows various types of traffic to travel on the same physical network, whether it would be voice or data or video, etc. There's some advantages to a converged network. It's just one network to manage, which makes it easier for the organization. It reduces overall cost because you're not looking at redundant cabling infrastructures, and it can provide additional functionality. When voice and data was on separate cabling infrastructures, integrating voice and with applications became very difficult, as well as video. With the emergence of converged networks, the convergence of these different types of functions is now much easier to develop and to manage. Just think of everything we do on the internet these days. So that's what a converged network is. On slide 1.1.1.3, Cisco talks about borderless networks. And borderless networks is essentially Cisco's marketing term implying that their networks can connect anyone, anywhere, anytime, and on any device. Sounds too good to be true, but conceptually it is possible on a Cisco network. The borderless network is based on two sets of services, network services and user endpoint services, and is built on a hierarchical infrastructure with policy-based software solutions. What that means basically is that they provide you the tools to do all this. The goal with all of this is to be able to optimize network resources, provide robust security, and allow for scalability of the network through growth. Within the borderless network, there's what they call the hierarchy. And the hierarchy is the way that Cisco kind of organizes the design of a Cisco network. What you have is an access layer, a distribution layer, and a core layer. The access layer is what our endpoints all connect to, and these are the switches that are going to be close, that our devices are going to directly connect into. Generally, you see these in cable closets in your general work area type of thing. And then you have a distribution area, and the distribution area is where the network aggregates the access layer switches, and this is where policies get implied and kind of directs where else traffic can go inside the network. In specifics, what the distribution layer does is aggregates large-scale wiring closet networks. So usually you'll have a distribution layer in a very large organization. It also aggregates all your layer 2 broadcast domains, or your VLANs. and we'll get into VLANs here in a little bit. It provides intelligent switching, routing, and network access policy functions to access the rest of the network. So this is where the intelligence in the network usually is. The core and the access layers are generally less intelligent in terms of the decisions that it makes. The distribution layer also provides high availability because it will dual home switches, as you can see in the switch here on the left. There's a connection to this distribution switch and a connection to this distribution switch, which provides some redundancy in having multiple paths to the core layer. It also provides differentiated services to various service applications at the edge of the network. So there are some applications that it can provide downstream to the access layer devices beyond the scope of this course. The core layer is what we call the backbone in most networks. The backbone is high speed and usually has minimal traffic policies so that it's as efficient and as fast as possible. It's kind of like the superhighway of the network. Now in a smaller network, no, I went too far here. In a smaller network, which you'll not find a distinguishable distribution and core network. That we refer to that as a collapse core, and that is where the switches at the core provide both the aggregation of access switches and for the high-speed transport of the core layer. So in 1.1.1.5, they kind of illustrate how this kind of pays off for us when you have a campus, a large campus or a large network. This modularity allows us to build networks with basically location-based core distribution and access layers at each of our locations. So this allows for a more scalable and easily modular environment for us to build and maintain our networks in. So the payoff of all of this is that the design guidelines that are brought forth in the borderless network infrastructure is that, again, as we discussed, that it's hierarchical and it facilitates the understanding of the role of each device at every tier. So we know what the basic functions of a device is based on where it is in the hierarchy of the design. This simplifies the deployment, operation, and management of each individual device. Also, it provides modularity, as you can see in this slide that we have up right now, and that allows for relatively simple network expansion. The resiliency that you can build into it with redundant links to distribution switches and from the distribution switches to the core, etc., allows for incredible resiliency of the network in that it is very tolerant to device failure. And with the management tools and the policies and all of the stuff that we can build into our network design, it allows for intelligent traffic load sharing by all network devices. So that's the sales pitch. Hope you liked it. So the role of switch networks here in 1.1.2.1 is that what a switch network provides us is it provides us of a high quality of service so that depending on our type of traffic that we are interested in, it gets there in a reasonable time frame without corruption or delay. It also, our switch networks provide us some additional security based on our policies and where we allow certain traffic to go with within the network, which we'll get into more when we talk about VLANs in Chapter 2. It also supports wireless networking and connectivity by adding wireless access points to our access switches. It allows us to extend our wireless network from the switch network. And it supports new technologies such as IP telephony, which is the integration of computers and voice, and also mobility services. Now, switches themselves. There's basically three types of switches out there. There's what are called fixed configuration switches, and these are lesser expensive. What you see is what you get. Ports are defined with density and speed and interface type, and you can't change them. They're um, like I said, relatively inexpensive on the low end of the switch spectrum. Modular configuration switches are a little more advanced. They give you some flexibility with line cards to allow you to mix and match different interfaces and speeds into the same chassis. So modular configuration switches are more expensive, but they do give you more flexibility. Stackable configuration switches are actually um, small modular configuration switches, or even some fixed configuration switches that allow you to daisy chain them and can be managed as a single switch using cross-connected connections. The network can recover quickly if a single switch fails, and these are popular in medium-sized networks. And stack power is a feature of these stackable switches that actually allows multiple switches to share each other's power supplies in the event that you have a power supply failure. So the considerations in selecting the switch, obviously you've got to look at cost, number one. The cost of the switch depends on a lot of different things. And you know, the type, the speed that you need, the interfaces, the supported features, and the expansion capability that you want within that particular switch. Port density is also very important. Network switches must support the appropriate number of devices on the network. A switch isn't going to do you any good if it hasn't got enough ports to hook everything up. Power is also a big consideration. IP phones and wireless access points, they are typically powered now over the Ethernet cable using PoE technology. Also, some switches have redundant power supplies. The reliability of the switch is also important. You know, the better the switch, the more reliable it's going to be. If you go with cheap switches, you're probably going to have more downtime. Port speed, the speed of the network connection is a primary concern for end users. So if you've got heavy users and you're using 100 megabit switches, then you maybe need to look at a faster switch in terms of port speed to handle the volume of traffic and avoid bottlenecks. Frame buffers is also important. A switch that supports frame buffers is important in a network where there may be congested ports and servers or other areas of the network. What frame buffers means is that the switch has the ability to store traffic in kind of a buffer so that it can and it holds it so that it can be transmitted out to the destination port as soon as it becomes available, as opposed to the sending or source device having to resend it multiple times. And then the scalability of your switch, allowing a little room for growth. So if you got 24 computers that need to be connected to the network on an access switch, you don't want to get a 24 port switch. You want to get a 28 or a 48 port switch so that you have room for growth. So how does a switch work? Well, a switch basically has, for any given frame that goes to it, it is going to go in an ingress port, and it's going to leave an egress port to get to its destination address. And the way that a switch works is it essentially populates a MAC address table. And slide 1212 and the couple and the figures that associated it with it really does a good job of explaining to you how exactly the switch keeps track of things. Remember that each network device out there in the universe has a unique MAC address, and but we communicate between computers based on IP address. So there has to be some mechanism of which IP addresses and MAC addresses get mapped. And the switch essentially does that for us at the local level in that it maintains what is called a MAC address table. And so what happens is that when a PC sends a frame that contains an IP address, within it a packet to a destination IP, it has a source and a destination MAC address. And if the MAC address is not known, it will send out a broadcast out the other ports, which I think they show in 3 here, that says, hey, I don't know who this is. Does anybody out there claim to be who I want? And then the one that says, yes, this is me, will send it back to the switch, and the switch will then populate the MAC address table so that the next time PC1 needs to communicate with PC3, it doesn't have to go through all that. The MAC address table will be there with that entry, and it'll just look it up and send it on quicker. So that's in a nutshell how a switch works. It's basically exactly what it says. It's a switch. It is managing traffic in one port and out a specific other port. And when it doesn't know what the specific other port is, it has a mechanism to go find out. So once the packet is received by the switch, or the frame is received by the switch rather, what happens once it's there? Well, it gets forwarded. Well, there's a couple ways that can happen. Cisco devices by default do what is called a store and forward method, where it receives the entire frame, does error checking on it, and if there's an issue, it will drop the frame. If it's good, then it will, once it determines the destination port, send the frame out. The cut-through method, by contrast, basically starts sending that frame out to its destination port as soon as that destination is known. The advantages of store and forward is that the switch is actually ensuring the quality and integrity of the frames that are coming in before it'll send them on. This does put more overhead on the switch. You need a more powerful switch from a performance standpoint to do this. Cisco switches by default do store and forward methods most usually, and whereas the cut-through method, although configurably, is not typically used. The benefit of cut-through method is it's a lot faster. So in 1221, we talk about collision domains and broadcast domains. And the beauty of switches is that each port is considered a collision domain. Back in the old days, we used to have what were called hubs. And basically every packet went out every port, or every frame went out every port. And so the switch often had frames collide with each other, causing network interference, if you will, or network noise, and a lot of retransmission of frames, and it was very inefficient and very slow. So when switches came along, it basically eliminated, in reality, the collision domain. We still have broadcast domains, though, within switches, and that's for multicast and unicast communications. I'm sorry, multicast and broadcast communications with multiple devices on the network. In Chapter 2, it starts off with the switch boot sequence of a Cisco switch, and this is something that you need to read through thoroughly and make sure you understand the concepts and what is found in each type of memory, etc. And some of the uh, uh, LED indicators and what they mean and that sort of thing. It's not tested on heavily, but it's something in practice that you're going to need to be familiar with. They talk about preparing for remote management and using a console cable and configuring a switch virtual interface, which is how you access the switch to be able to manage it. So we get into configuring uh, basic switch configuration, and you have what a concept called duplex communication, and basically the traffic on any Ethernet connection can flow full duplex or half duplex. Full duplex means that data is moving both ways simultaneously, which is the default on Cisco devices, as well as most PCs, and half duplex is really an obsolete concept. But the thing that's important to know is that if you have a port configured as half duplex for any reason, like you got a legacy switch or something like that that you need to connect to a Cisco device, the ports must match on both sides. And this goes for other concepts such as port speed. So if you're running at auto on both, you're going to be fine. But if you're running at 10/100 on one and a gigabit on your other switch, and those speeds don't match, you're going to have problems. Also, MDIX auto. That's a concept that um, almost everything is MDIX auto now, but when switches first came out, and networking devices in general, the general rule was that if you had two devices of the same type, they could only communicate through a crossover cable, which is a network cable, but it's basically has, I think, pins 2 and 3 switched or crossed over. The MDIX on a port basically allows it to be smart enough to know that it needs to switch the communications there. So that made life a lot easier, so you weren't always digging for that special cable to get things to talk. And they get into switch port configuration and some of the verification commands that are out there. You really need to know these and understand them and what is contained in each, because you do get tested heavily on those in the chapter exams and on also the final. They talk about network access layer issues and how to troubleshoot by looking at the network interface status using the show interfaces command. That's a good thing to make sure you understand what's going on there. Nice little troubleshooting diagram there that is good to kind of help you sort through things. Might be a good thing to take a snippet of and put it on your desktop so that if you're trying to troubleshoot issues, you can do that. Then on slide 2.2.1.1, they start talking about secure shell. Now, secure shell is the protocol that we use to securely manage our network devices. Secure shell is a supported protocol on most terminal emulation programs such as PUTTY and TinyTerm and things of that nature. You do not want to manage your devices using Telnet. So you want to make sure that when you configure port security that you only allow for secure shell access to your Telnet ports and even your console ports. So that that's just a best practice. I know a lot of people that will allow terminal emulation on the inside of their network, but only secure shell from the outside. I think it's too easy to kind of forget something, and it does open you up to internal, misfits that want to try to hack into your equipment and cause problems. Now, so they go through how to configure secure shell, and there's a packet tracer on how to do that and how to verify it, etc. Then we get into some common attacks that we see on switches from a security standpoint. The first one that they talk about is MAC address flooding, and MAC address flooding is when a hacker takes advantage of the fact that MAC address tables are limited in size. What happens is they overwhelm the switch with fake source MAC addresses on frames that they create and send to the switch. And what happens is the MAC address table just starts to get overwhelmed and fills up. Now there's ways that we can mitigate that with security port security configurations, which we'll get to later. DHCP spoofing is a similar type of attack, and DHCP spoofing, if you remember, DHCP is the protocol that basically determines what an IP address a client network gets, and in DHCP spoofing attacks, an attacker configures a fake DHCP server on the network to issue IP addresses to clients. The normal reason for this attack is to force the clients to use false domain name systems or Windows Internet Service servers to make the clients use the attacker or a machine under the control of the attacker as their default gateway. So it's basically a way that a hacker can force traffic to get redirected to where they want it to get redirected to. And then leveraging CDP is another one that they talk about. And CDP stands for Cisco Discovery Protocol. It's a Cisco proprietary protocol used to discover what other Cisco devices are directly connected to a device. And in some cases can auto-configure the connection. And this is a bad thing that Cisco's done here, in my opinion, because basically what it's done is it's provided a protocol to give a hacker all the intelligence they need to be able to figure out a way to cause havoc on your network. So my recommendation is that you disable CDP on any device that you have, and that no CDP run global configuration command will take care of that. So best practices are listed here, and read through these. Some of these are common sense. Some of these are specific configuration tasks you should plan on doing. One thing: shut down unused services and ports. Don't allow a switch to do something you don't need it to do. Use your strong passwords for your management passwords. Don't make them password, or even the name of your dog, or even your birthday, because that stuff can be obtained. Your switches should be in physically secure places that are lockable. You don't just have your switch out there in a hallway or in a janitor's closet or something like that, because your switch is the physical access to your network. Make sure your configurations are backed up. That's a big deal. Because if that switch would go bad, you're going to have to build that configuration from scratch, and if that configuration is rather complex, that could be significant downtime, and that could be your job. Educate employees about social engineering attacks and develop policies. That's, again, common sense stuff, as well as encrypting and password protecting sensitive data. This is general network or IT infrastructure best practices. Make sure you have security hardware in place, such as firewalls and keep your software up to date so that any security vulnerabilities that have been uncovered are resolved. So we go into securing unused ports and the configuration commands related to that, how to mitigate DHCP snooping by putting those commands into your switch, different port security operations to help manage the MAC address table so that you don't get MAC address spoofing. That's all covered in here. And then, you know, the one thing that's important to know is the different violation modes, so that if it does, uh, uh, you know, detect an unauthorized or too many MAC addresses on a particular port, what is it going to do with that port? Is it going to protect the port? Um, is it going to protect the port, restrict the port, or shut down the port? And those explanations are here for you to read and to learn. So we go into verifying port security, knowing if a port's in a disabled state. Also, and there's a bridge exercise on this on configuring NTP, which is the network time protocol. It's important that all your, from a logging standpoint, all your switches in your network are all on the same time. And using an NTP server basically allows all your network devices on a network to be synchronized. Your Windows servers and all those other things that are on your network should also be doing this, and your client should be getting your time from a NTP server in some way, either through a server that's talking to an NTP server, or through a network device that is talking to an NTP server. So everything on your network should be precisely at the same time. Otherwise, strange things can happen. Okay, Chapter 3. VLANs. VLANs are are a way for administrators to segment networks based on factors such as the function of the specific clients on the network, or for a particular project team or an application without regard to the physical location of the user or device. And segmenting a network also allows us to create multiple broadcast domains. You can think of it as creating sub-switches on a switch. It also improves security in that devices on one VLAN cannot see another VLAN through NetBIOS or other computer searching type protocols. It does improve performance in that it does reduce your broadcast domains, so there's not as much traffic hitting all the clients. And as a result of all this, and through simplified IT management, as far as IT resources, it does reduce costs. There are several VLAN types that are out there. There are data VLANs, which are, you know, your normal VLANs that handle your computing data, traffic between your clients and your servers, etc. A switch has a default VLAN, which is VLAN 1 on Cisco devices, and oftentimes the data VLAN is also the default VLAN. There's an argument as to whether you should or you shouldn't change your data VLAN to be a different VLAN. I think it really just depends on the size of your network and how concerned you are about overall network security. But best practice is that your data VLAN should not be your VLAN 1. Basically, VLAN 1 shouldn't have anything on it. But again, in practice, often you'll see the VLAN 1 as your data VLAN. The native VLAN is related to trunk ports. Basically, trunk ports are ports between switches that carry VLAN traffic between switches. And if a VLAN is a tag, a VLAN tag is um, on traffic or I guess I should reword that. Tr on trunk ports, VLAN traffic is tagged, and if it is destined to be on a VLAN. If by chance there is a frame that hits the switch that um, is not tagged, it is considered untagged, and that will be assigned to the native VLAN. Again, the native VLAN by default is VLAN 1. Best practices is that you make it some other VLAN number. A lot of people will make it 99 just to put it way out there, out of the way. The management VLAN is often implemented to allow a separate VLAN for remote access of switches so that the users, even if they had secure shell and they had all the rest of the information, because they're on a data VLAN, would not be able to get to the switches and manage the interface. Only computers in the data center or in the support center would actually be able to physically get to the VLAN, the management VLAN. Again, by default, it's VLAN 1, depending on the size of your network and the sophistication of your users, etc., your tolerance and your risk tolerance as far as security is concerned. You may have your management VLAN be on VLAN 1, but in larger networks it usually is not. There's also voice VLANs out there, and voice VLANs are VLANs that are set up to handle voice traffic. And the reason why we have voice VLANs is because we need to set the quality of service on those particular VLANs to ensure that voice quality is there. It gets voice transmission priority over other types of network traffic, and it allows us to route it differently than other traffic on the network. So a little more about VLAN trunks. VLAN trunks are, again, basically links between switches that carry VLAN traffic, and it uses the 802.1q standard, and VLANs basically are the conduits to allow VLAN tag traffic to move across the network and get to the access devices that need that particular traffic. You can have as many VLANs as you want. You can have multiple data VLANs. You can have multiple voice VLANs. It just makes your configuration more complex. Typically, as they show in this example, you might have a VLAN 10 for your faculty, a VLAN 20 for your student, and a VLAN 30 for your guest, being that the faculty would probably have needs to have more access to very secure resources that students would not need access to. Um, and guests would not even need access to the same resources that students have access to, but they all need internet. And through the VLANing and VLAN trunks and gateways or routers, we can make sure everybody gets what they want, but they can't get into each other's business. So they go through a pretty good discussion about VLAN tagging, and this is good to know. It's very important that you understand the concepts of tagging and trunking and how all that actually functions. So they go through configurations of creating different VLANs and how to change port membership of an access port from one VLAN to another. And these are all pretty heavy configuration commands, and there's packet tracers and labs that take you through that. If you apply yourself and put the time into understanding these configurations, you'll start to get the feel of how you're controlling the switch as far as what it can do and what kind of traffic it can handle and manage. So the next subject we want to talk about is dynamic trunking protocol, or DTP. Don't use it and shut it off if it's on. If you get into a network where they're using dynamic trunking protocol, get rid of it. Um, dynamic trunking protocol is basically the ability for switches to auto-configure their trunk ports. And you can imagine that, well, if you can auto-configure a trunk port, then somebody could plug a switch in, and if it's plugged into, if the switch it's plugged to on the other end is auto-configuring trunk ports, now that rogue switch I just added to the network has access to all my VLANs. So for example, if this was my switch here that I brought in from home, and this switch is configured for dynamic trunking protocol, I could plug this switch in, it would build a trunk port, and which means that I got a path to all the VLANs that are allowed on that switch. So that would not be a good thing from a security standpoint. This table on 3.2.3.2, you need to really kind of commit that to memory, which is these are the different modes. So if this is the modes for switch 1 for dynamic trunking protocol, and these are the modes for trunk 2, by combining these two, you know what how the port is going to act. It's going to act. So, for example, if I have switch 1 set up as a port with dynamic desirable, and it is set up to plugged into another switch that the port is configured as dynamic desirable, it's going to build a trunk port. Whereas if it's dynamic auto on one switch and it's dynamic auto on another, it won't configure a trunk port. It'll just consider it an access port. So understanding this table will help you be able to look at a given scenario and be able to determine whether or not it's going to create a trunk port or not. And you can look at the status of DP interfaces on a particular switch using the show DP on an interface, specific interface. So that's a little bit about DTP. Not a big fan of DP. This little exercise here helps you predict, is an exercise to help you predict uh, um, what's going to happen given the trunk port configuration or the DTP configurations of particular ports connected to other switches with particular configurations on those ports. Okay, some attacks that VLANs can deal with. There's a switch spoofing attack, and switch spoofing attacks are attacks that um, an attacker takes advantage of the fact that default configurations of the switch port is a dynamic auto, which is why I tell you to make sure that you've got DTP disabled. The network attacker configures a system to spoof itself as a switch. The spoofing requires that the network attacker be capable of emulating 802.1q and DTP messages. By tricking a switch into thinking it's another switch and attempting to form a trunk, an attacker can gain access to all the VLANs on the trunk port, which is what we talked about earlier. Another common attack is double VLAN double tagging. That's where you encapsulate a frame inside of a frame. And so that it's kind of like a Trojan horse. You've got a bunch of VLAN 20 frames inside a VLAN 10. You have a VLAN 20 frame encapsulated inside a VLAN 10 frame, so that maybe you're authorized to send a VLAN 10 frame through a particular link, And then when it gets to the other side and it decapsulates it, now I've got a VLAN 20 frame running around. So that's the method of double tagging. Another thing that this isn't really an attack, but really a way that you can kind of better protect your network, and that is PVLAN Edge, or otherwise known as protected ports. If you don't want any traffic under any way, shape, or circumstance to be able to go from one port on a switch to another access port on the switch, you can make those switches protected. And then you only make the port on the switch unprotected of which you want the data traffic to be able to egress out. So if you've got a server up here and you have two clients, you can set those two client access ports as protected and the server port is unprotected. That way you're only allowing traffic back and forth in this manner or in this manner, but you're not allowing any traffic back and forth in this manner. That's PVLAN Edge, and they have commands here on how to do that as well by configuring them as switch port protected or switch port or no switch port protected, depending on whether you want a particular access port on a switch protected or not. Okay, so that is just a quick overview of chapters 1 through 3. Again, this isn't to spoon feed you on everything you need to know, but my hope is that this will give you the theoretical or conceptual framework so that what you're reading makes a little more sense. I'm going to try to be a little bit ahead of the game from here on out and getting these out for you as we're going through the coursework. I know with the beginning of the semester it's been pretty much nuts and chaos as usual. So, but anyway, look more for more of these to come. Thank you.